We have the pleasure to have Riccardo Pengo from Lyon, who will speak about Mahler measures, special values, and exactness, a periodic journey. Please,
Thank you.
Riccardo.
Thank you very much, Thiago, for the introduction, and thank you, Hossein and Younes, for the invitation to give a talk in this very nice seminar. So today, indeed, we are gonna see some relations between Mahler measures, which, as I will recall, is a concept sort of which was born in transcendence theory, and which has a very number theoretical origin, and special values of all functions, which are also very arithmetic, and then this notion of exactness. So exactness will be a notion which would refer to polynomials, which has been introduced by the work of Vincent Maillot, and that François Brunault and myself are trying to sort of contextualize, and sort of we are giving in this project a new definition of this concept, and also we are introducing or rather precising the notion of successive exactness for polynomials, and I will try to explain to you these concepts. But since the backgrounds, I think, are kind of varied, I will start by an introduction on what is the Mahler measure, its definition and basic properties, and why we care about exactness, indeed. And so here I've entitled this section from Darboux to Lyon, because as we will see, these some key tools in the notion of exactness may date back even to Darboux. And then in the last section, I will try to tell you about our project, what we are doing, and what we have achieved so far. Okay, so let's start. So this is a seminar about periods, after all. So I wanted to start with periods. So as I think all the people in this audience know, periods are complex numbers which admit many equivalent characterizations. Here I've chosen three. So first of all, you can define them elementarily. So a complex number is a period if and only if its real and imaginary part are up to sign volumes of semi-algebraic sets. So this is a very concrete, hands-on definition that you can use also computationally to sort of really compute the real and imaginary part of this period. Then there is the notion, the definition given by Konstevich and Zagier. So a complex number is a period if and only if its real and imaginary part are integrals of rational functions over semi-algebraic domains. And then there is a third characterization, which is so-called, well, which here I have called motivic. I guess nowadays it's more or less standard definition, but I mean, this is a very vague sense. So you can say that a complex number is a period if you can express it as the pairing. So here, these little brackets here denote the Grothendieck pairing between the RAM cohomology and Betti cohomology on a smooth variety X relative to some divisor, which you can assume to have simple normal crossings. Okay, so you have the RAM cohomology class, and you quote unquote integrate it along a Betti cohomology class. Okay, so this really comes down to usual integration if, for example, X is affine. Okay, so as an example of these three different descriptions, of course, the first period that one learns about is pi. So, and also 2 pi I, for example, is a period. If you want to see 2 pi I is a period, well, you can see, so it's a purely imaginary number, and its imaginary part is twice the volume of the unit circle. So this is the first definition, so as an elementary period. You can also give pi as an integral, indeed, of a rational function over sort of the empty condition, so over all the real line. And indeed, you can see pi cohomologically, for example, by integrating dz over z over a small loop around 0. So this integral, you can think of it as taking place inside GM. Oh, sorry, here there is an M which should have gone downstairs. Okay. All right. So a a problem that one may have is if I give you a period, and usually these to show that a complex number is a period, maybe it's the easiest to use the Konstevich and Zagier definition. We have so many integrals that we care about. So maybe you have a period expressed as an integral. So then you want to actually express it as a motivic one. So essentially you want to write it as a pairing over a smooth variety defined over Q. And so why is this interesting? Well, for here, I sort of gave two reasons. The first reason is that this can allow one to make predictions about transcendence via the period conjecture. So it's easier to study. So for instance, one can study the action of the motivic Galois group over the period using a motivic description. And then maybe this allows one to place our period, quote unquote, in various filtrations. What do I mean? Well, if we have eta and gamma, then we can sort of consider various filtrations on these cohomology and homology groups. For example, they carry a mixed dodge structure, so they carry a weight filtration, and it's usually interesting to study the places of these eta and gamma inside this weight filtration. Okay, so today we are going to see this framework, to apply this framework to the Mahler measure of a polynomial. So as I promised, here is the definition. Okay, so the Mahler measure of a polynomial is something very simple, which was indeed introduced by Kurt Mahler in 1962, but as we will see, it actually dates back further, much further. So if you have your favorite complex polynomial, well, it had better be non-zero for what we're about to do. Then you can just take the logarithm of its absolute value. So this is a function which is well defined everywhere where the polynomial is non-zero. Then it has logarithmic singularities when the polynomial vanishes. But it turns out that you can always integrate it over the real unit torus, so S1 to the n. Okay, you can integrate it against the Haar probability measure, which is given by this formula on the real unit torus. And it turns out that this integral always converges if your polynomial is non-zero, and it gives rise to a real number that we call the Mahler measure of P. Okay, so why is the Mahler measure interesting, and why was it studied? Well, it's interesting because it sort of sits in the middle between two kind of invariants that you can associate to a polynomial. So usually in number theory, one is interested in polynomials with integral coefficients. So if you have a polynomial with integral coefficients, you can associate to it some more arithmetic invariants or some more analytic ones, okay? So for analytic invariants, you would like them to be related to analysis, and so indeed, the Mahler measure is related to analysis because it turns out, for every complex polynomial actually, that it is the logarithm of the limit for p which tends to 0 of the LP norms of your polynomial computed over the unit torus. Okay, so this is something which appears also elsewhere, and sort of it allows you to really relate the Mahler measure to the analysis of the analytic properties of your polynomial. But also it has an arithmetic flavor. Why? Well, because if your polynomial turns out not to be irreducible, then you can actually decompose the Mahler measure. So the Mahler measure of a product decomposes as the sum of the two Mahler measures, okay? This is simply because you have a log inside, okay? Moreover, what happens? So it turns out that indeed the Mahler measure is related to a quantity which has somehow a very arithmetic flavor, which is the length of a polynomial. So simply the sum of the absolute values of its coefficients. And it turns out that the Mahler measure is essentially the same order of growth as the logarithm of the length. Okay, and so using this fact, which is true for any complex polynomial, since any integral polynomial has length at least 1, this implies that the Mahler measure of a polynomial with integral coefficients is always positive. Okay, and why is this interesting? Well, because when you have something which is positive, then it's usually interesting to sort of, I mean, we can consider the Maillard measure as a functional. Now we have seen that it is positive on integral polynomials. So can we compute its minimum? And indeed, it turns out that one can. So this is due to Lawton and this generality from 1977, but actually generalizes a result of Kronecker from much, much earlier. Who did it for polynomials in one variable. And it turns out that the answer is, if you have a polynomial with integral coefficients, then your Maillard measure vanishes, if and only if the polynomial is up to a monomial, a product of cyclotomic polynomials. So here the phi I are cyclotomic polynomials evaluated at some monomials. Okay, so here these notations zeta n to the vj. So yeah, I haven't said it, but as it's more or less common, zeta n is the tuples zeta 1 up to zeta n, and zeta n to some vector v is the monomial zeta 1 to the v1 up product until zeta n to the vn. Okay. And here, when I say polynomial in this talk, I will always mean Laurent polynomial. So we allow negative powers. This is somehow not so important because it turns out that the Maillard measure of a monomial vanishes, and by the property displayed here, you can always get rid of denominators. Okay. So why was the Maillard measure introduced in the first place? Well, this goes back much earlier, as I said. It is due to Peirce in 1917. He was interested in finding big prime numbers. So what's more number theoretical than that? Finding big prime numbers, okay? And he wanted to generalize the notion of Mersenne prime. So when you know that primes of the form 2 to the n minus 1, or actually numbers of the form 2 to the n minus 1, for n prime, they have some chance of being prime. They're not always prime, but they have some chance. And the interesting thing is that you can factor them much more easily than you do for general integers. And this phenomenon generalizes. So more precisely, if you have a polynomial in one variable, then you can form from it a sequence of integers. Let me call it delta n of p by multiplying the nth powers of its roots minus 1. So minus 1 here is inside the product, so each factor is minus 1. And what happens is that these integers are much easier to factor, so they satisfy various congruences conditions that allow you to factor them much more easily than a random integer. And in particular, what happens is that you can look for primes in this sequence. So you're interested to see whether this sequence grows like crazy, or it's actually feasible to compute it up until n equal, I don't know, 100 or 1000. So actually back then, I think they managed to compute it by hand up to n equal 300 or something for polynomials of degree 3. And so anyway, so how does this quantity grow? And this is the insight of Lamer from 1933. He showed that this quantity grows geometrically, essentially, and the ratio between one term and the next converges indeed to the exponential of the Maillard measure of P. Okay, so at least this is true if P has no roots on the unit circle. Okay, so indeed, we want to, so indeed he said then it's an interesting problem to find the smallest Maillard measure which is positive, because if the Maillard measure is not positive, then you're not getting much. It turns out, I mean, these numbers will sort of be periodic because these polynomials will be cyclotomic. So we want a Maillard measure which is non-zero, positive, but as small as possible. So does it exist? In other words, is 0 an isolated point of the set of Maillard measures of polynomials with integer coefficients? And he asked, so he said in the paper that the polynomial with the smallest Maillard measure that he could find was this very sort of strange-looking 10-degree polynomial. Okay, and surprisingly enough, it's still open to this day. So to this day, we don't know whether the Maillard measure has, so whether 0 is an isolated point or not. And even more, we don't know any polynomial whose Maillard measure is small, even one variable whose Maillard measure is smaller than this one. Okay. Great. So why are we? So why? So what can one do if one wants to try and solve Lamar's problem? Well, one of the most interesting strategies, in my opinion, is due to David Boyd. So he said, why don't we look, now that we have the definition of Mahler for the Mahler measure in multiple variables, why don't we look at polynomials in multiple variables? And why is this interesting? Well, because it turns out that each Mahler measure of any polynomial in multiple variables is a limit point of Mahler measures in one variable, okay? For instance, here I have written one possible sequence of Mahler measures in one variable that you obtain by substituting, by doing monomial substitutions inside your polynomial, which indeed converges to the Mahler measure of your polynomial in any number of variables. Okay, so it turns out, and I guess that here it should be n-1, sorry. And so here, okay, so now this shows in particular that if you call Mn the set of Mahler measures of polynomials in n variables, and M infinity the Mahler measures of polynomials with integer coefficients in any number of variables, then it turns out that, well, this M infinity is contained in the closure of M1, because each Mahler measure is a limit of Mahler measures in one variable, okay? So in particular, a very easy argument, since this is also semi-group, because, I mean, of this multiplicative property that we've seen, a very easy argument shows you that if Lamar's question has a negative answer, so indeed, if we don't have this minimal positive Mahler measure, then it turns out that the closure of M1 is equal to the whole real positive line, okay? So in particular, if by any chance this M infinity is closed, so if limits of Mahler measures in any number of variables are always Mahler measures, then Lamar's question, or at least a weak version of it, so this question about does there exist a minimal positive Mahler measure, has a positive answer, because, I mean, you just do the contrapositive of what I just said, okay? And so now the interesting question is, why should we expect M infinity to be closed? Well, here is a very interesting result of Smith from 2018. So this is quite more recent. So if you take, for any polynomial, let me denote by PA, the polynomial that I obtain by doing monomial substitutions inside it, and these monomial substitutions are governed by a matrix A. Okay, so here is the formula that one can actually use. And so if you do so, if you use these monomial substitutions and you start from a polynomial, you take the orbit of this polynomial under these monomial substitutions, and then you take the Mahler measures of these, you can form a set of real numbers, call it curly MP. Then it turns out that this set is closed, okay? And this is due to Chris Smith. And moreover, M infinity is filtered by sets of this form. Because, well, simply you can do monomial substitutions to reach any polynomial that you want. Essentially, you just need one positive coefficient and one positive coefficient and one negative coefficient, and then you just do as many substitutes. For example, if you have -3x appearing in your polynomial, you just take 3 of these. You take 3 new variables, and you will apply a monomial substitution of this kind. Okay. So anyway, so M infinity, we don't know whether it's closed or not, but it's filtered by closed subsets, which is already something interesting. And so let me mention very briefly that we have another project with François and 2 other collaborators, Antonin Guillouf and Maillot and LalÃ from Paris, and they and we are we have generalized this theorem of Boyd and this theorem of Boyd, which was also already generalized by Lawton, to consider more general sequences of one variable Mahler measures, which converge to n variable Mahler measures. And here we do any number of variables. So here we take any monomial substitutions. And in particular, we show that indeed, if you take a sequence of matrices where this invariant vanishes, so where the smallest vector that is in your kernel tends to infinity, more or less, then this essentially means that the corresponding subtori of your unit torus will equidistribute. And we proved that this is enough because the equidistribution is good in some sense. This is enough to indeed get that the limit of the corresponding Mahler measures converges to the Mahler measure that you start from. And as a special case, we recover an identity proved by Maya in her PhD thesis, where she looks at and she gives a different proof of this identity, looking at the limit of the Mahler measures of these polynomials PD, which have a very particular shape. They're just polynomials in two variables, summing up all the monomials with bounding exponents, with the exponents bounded by some integer d. With degree bounded by some integer d. And notice that these polynomials will be examples of exact polynomials, as which is a notion that I'm just going to introduce next. Okay, so this is somehow the general theory of the Mahler measure. And now let's move to these more arithmetic connections. So the connections with special values of L functions. So as we have seen, it's interesting to look at multivariate Mahler measures. And in particular, it's interesting to look at the small multivariate Mahler measures. So that's exactly what Boyd started to do when sort of computers started to, be powerful enough to do this kind of extensive searches. And so he did this for some part of the 90s, I think 40 years or so, and then he published his results in 1998. And in particular, he found this very symmetric family of polynomials. Okay, with k, which is a parameter which varies, you can take it to be the square root of an integer. And he found that this Mahler measure turned out to be numerically related up to a rational number to the derivative of the L function of some elliptic curve at 0. And what's this elliptic curve? Well, it's simply given by this polynomial, let's call it pk, equal to 0. Okay, this gives you some elliptic curve. Or actually, I mean, you can take the 0 locus inside gm squared, then you will have some elliptic curve minus some points, and it turns out that these points at infinity don't matter. And what you really get, what seems to be appearing here numerically is this L value of an elliptic curve. Okay. And so today, these identities are known for a finite number of values of k. So here I hope to have a complete list, but every time I give a talk, someone tells me that there is some value missing. So please, if you see a value missing, let me know. And this is due to many people. So Rodriguez-Villegas treated the values of k for which the elliptic curve has complex multiplication. Then Rogers and Zadilin, they introduced a method to compute L values of products of Eisenstein series, which sort of allowed them to solve. So I mean, actually, they did this, and they also solved the case k equals 1 of the conjecture. And then François Brunault generalized this method to regulators of Siegel units, and so many other people contributed to the effort, who are hidden in these etc. Okay, so but what I would like to draw your attention to today is the fact that actually these identities can be related to Beilinsen's conjectures. Okay, so if you're interested in periods, you know that Beilinsen's conjectures can be essentially phrased. I mean, a very weak version of them can be phrased by saying that special values of L functions of arithmetic objects should be periods. Okay, so this is one version of Beilinsen's conjectures that you can find, for example, in the paper of Konstevich and Zagier. Okay, so now the idea is that here we don't want them just to be periods. We would like them to be a very special kind of period, namely a Mahler measure, the Mahler measure of a polynomial. And how do we do this? Well, it turns out, as Christopher Deninger showed in 1997, that the Mahler measure can be computed as a period in a very specific way. So basically, what you do is that you take a certain symbol Z1, Zn. This symbol, if you know what it means, is taken in the motivic cohomology of Gm to the n, and this is why one uses the multiplicative group, because you want the variables to be invertible, okay, in order to take this symbol. If you don't know what it means, don't worry, because then you want to take its regulator, okay? So if you take its regulator, what you're left with, it's essentially a very explicit differential form, okay? Which, for example, for n equal to 2 looks like the logarithm of Z1, the derivative of the argument of Z2, minus the logarithm of Z2, the derivative of the argument of Z1, okay? So you're left with a very specific real analytic differential form. And what you can do is that you can, it turns out that there exists some cycle, and you can take as a cycle essentially the intersection of the zero locus of your polynomial with this semi-algebraic set. So this set where all the coordinates have absolute value 1, except the last one, which has absolute value smaller or equal to 1. Okay, and so if you do this integral, then what you get is essentially the Mahler measure up to a small correction factor, which is also a Mahler measure, but of a polynomial with one variable less. And actually turns out that you can essentially forget about it, because up to transformations which do not change the Mahler measure of P, you can assume that these coefficient is essentially the logarithm of some algebraic number, okay? Or even the logarithm of some integer if your polynomial has integer coefficients. Okay. Anyway, so we have this way of expressing the Mahler measure as a period in a very explicit way. And so, in particular, if your variety VP is smooth, okay, and your polynomial is tempered, which is a technical condition, it will come up maybe later, but it essentially means that these classes that you are defining on your variety, on your variety VP, which is defined in Gm to the power n, so it's not compact, actually extend to some compactification. Okay, so if VP is smooth, these classes extend to some compactification, and the boundary of this Deninger cycle gamma p is empty, then Bayes-Nelson's conjectures predict that the Mahler measure of P should be related somehow to a special value of an L function. So here I am being bold. So here I've taken the L function of something which, I mean, it's some cohomology. You can take it to be some L-adic cohomology of a smooth compactification of VP. So this will be a smooth improper variety. And I'm taking I mean, here I'm taking the L value at 0, which may not exist. So you may have to assume that your function analytically continues until 0, or you just take the value at n, which is what should be related to the value at 0 by the functional equation. But then you will have some correction factors. And here, this relation in the middle is very vague. So precisely what happens is that your Mahler measure will be, or should be, a rational multiple of one of the entries of the period matrix whose determinant should be equal to this special value according to Bayes-Nelson's conjecture. Okay, so this is actually what is happening sort of under the hood. And one last thing that I would like to say is that in Deninger's approach, and this would be important in what comes later, notice that here we have, so we can express the Mahler measure. I mean, I said that we can express the Mahler measure as a period, but this is slightly misleading, because, I mean, this is not quite displaying the Mahler measure as a motivic period, because we are integrating something. When integrating a differential form defined over VP, this is no problem. VP is an algebraic variety, but we're taking a homology class which is relative to something which a priori is not algebraic. Okay, so it's a semi-algebraic set, or rather an algebraic set, but it's not algebraic in a complex sense. Okay, because indeed it comes out from this intersection with the unit terms. Okay, and so this will be important later, because later we will see how to express the Mahler measure as a honest period. Okay, so very briefly, let me go through.
Riccardo, one
yeah.
question. Have these people also computed the cusp form attached to this EK elliptic curve for examples of K?
Yeah. So, I mean, I can't remember on the top of my head. So for K equals 1, it has conductor 11 or 14 maybe, yeah. And yeah, I mean, you can compute the conductor very easily, and actually, yeah, indeed, essentially all these proofs in the non-complex multiplication case deal with the fact that one can express the modular form explicitly enough as sort of linear combinations of products of Eisenstein series. And then one can apply this trick or method of Rogers and Zudilin to compute the appropriate integrals.
Okay, thanks.
Okay, so yeah, let me go very briefly through these things. So how can one really see sort of use Bayesian conjectures? So what turns out is that, so this is already in Deninger's paper in 1997, and then it was sort of explored, or like the details were written up by his student Brunault in 1999, that Bayesian conjectures imply that this relation holds. So under Bayesian conjectures, indeed, this Mahler measure is a rational multiple of the right-hand side, okay, for every value of K whose square lies in the integers, okay? And this can be generalized to other families. So this hasn't been done so much in the literature. So I have done it to illustrate the method for another family. And if you're interested, you can find the discussion in my PhD thesis, okay? And oh yeah, by the way, I will maybe later send the slides in the chat, and all these red references are clickable, and they will send you to the appropriate reference. Okay. Right. So, and finally, so one can take this one step further. More precisely, if so, we know for some kinds of varieties, we know a weak version of Bayesian conjectures. So essentially, I mean, think about the BSD conjecture. If you want, in the BSD conjecture, we know nothing about the rank part, but sometimes we know something about expressing the special value as a suitable regulator, okay, or a suitable multiple of a regulator. And this is exactly the case. So for L prime of E naught, we know something for elliptic curves with complex multiplication. We know that we can express it as a regulator. This is due originally to Bloch in his Irvine lecture notes, and this later was sort of detailed by Rohlrich in 1987. And one can use this, and I have done this also in my PhD thesis to show that the Mahler measure. So for every elliptic curve with complex multiplication defined over the rational numbers, you can find a polynomial. So you can find a model, a planar model of your elliptic curve, which may be singular, but you can find it, whose Mahler measure is rationally related to L prime of E naught up to the logarithm of an algebraic number. And these two RNS are very explicit, and they depend on the arithmetic of your elliptic curve E. And also the polynomial is sort of more or less explicit. I mean, there is a recipe to construct it. The problem is that it's defined as a minimal polynomial of some functions on E, and so it can have very big degree. And okay, it's not maybe super interesting to look at what the polynomial is, okay? Right, so this was just to mention very quickly what one can do with Bayesian conjectures, okay, in relation to the Mahler measure. But now let's finally get to the main part of the talk, so to the exactness condition for polynomials. Okay, so in order to motivate exactness, let me show you a gallery of explicit examples, okay? So Riccardo Rodriguez-Villegas is one of the masters, I think, of these explicit computations. And so here are, and his student, his former student, Mathilde Lalline is also. So here are some examples. So they start actually far back, much earlier than Boyd or Deninger. In 1981, Chris Smith found out that the Mahler measure, so he computed the Mahler measure of some polynomials, and among these are two linear polynomials. So these are the simplest polynomials that you can think of. And here, of course, there is a typo. So Ln should be this plus 1. Okay. So for example, L2 is Z1 plus Z2 plus 1. And it turns out, either this, okay, for J, which goes from 1 to 1. And so it turns out that the Mahler measure of L2 is also an L value, but it's an L value associated to a Dirichlet character. So this is the Dirichlet character, the quadratic character associated to the imaginary quadratic field Q was square root of -3. Okay. And it turns out that if you go if you take one variable up, then you get a special value related to Riemann's zeta function. Okay, and this is quite surprising because if you think about it, these polynomials are in two interior variables, so they define objects which geometrically have dimension 1 and 2 respectively. But so the hypersurfaces defined by these polynomials, but we are getting L functions associated to objects of dimension 0. Okay, and so this is precisely where exactness comes in. And so the reason of this dimension drop is precisely exactness. And so in particular for L2, the dimension drops once. And so one would like to say that the polynomial is 1 exact. Whereas for L3, the dimension drops twice. And so we would like to say that the polynomial is twice exact. Okay. And so I am going to explain to you this in the next slide. Okay. But before this, some more examples. So first of all, Ray in 1987 in his PhD thesis in Maillot and Rodriguez-Villegas, they computed many more of these. So many more Mahler measures related to derivatives of special values of special values of Dirichlet characters for imaginary quadratic characters. Okay, and then there is an interesting computation of Mathilde Lalin from 2006, which, as far as I know, is the only computation still available to this day for Mahler measures in any number of variables. So he computed the Mahler measure of this polynomial here in 2k plus 1 variables. He actually did it for also for the other family where you take S 2k plus 1. Okay, so you take odd number of variables in S. So S is this very explicit product of very simple expressions in these ZJs. And what turns out to happen is that this Mahler measure is an explicit linear combination of derivatives of zeta and even negative integers. So this is related to odd zeta values, which are notoriously very difficult to compute and very interesting conjecturally transcendental numbers. Okay. And so let me notice one thing, that so in these examples for 2 exactness and 3 exactness, we have, so here the Mahler measure is related to by the functional equation to a value at s equal to 2, and here to a value at s equal to 3. So you may think that always the Mahler measure will be related to a value for s equal to n, where n is the number of variables. But I mean, this is not always the case, because you can have some sort of phenomenon of residues appearing. And this is what happens, for example, in these instances computed by Deninger and LalÃ, which, by the way, is also the limit of the Mahler measures of the polynomials PD that I introduced before, and which were considered in Abdullah's thesis. Okay. So, but now, okay, of course, zeta values are very interesting, etc. But I mean, can we go up in dimension? So what about higher dimensional functions? Do we see them appearing as well? And indeed we do. For example, if we go up with linear polynomials, then we see that for 4 variables and 5 variables, we obtain conjecturally, so these are not proven identities, but you can check them numerically, the L values of some modular forms of weight 3 and 4 respectively, and here I've also written the levels, which are also cusp forms. And this is related to the fact that there's some variety, and I will explain it to you in a sec, that you can construct from these polynomials. Indeed, it turns out to be a model of a Calabi-Yau variety, which is related to these modular forms that are written here and that have been found by Rodriguez-Villegas in 2004. Okay, so the question, of course, is now we have Ln for n equal to 2, 3, and conjecturally 4 and 5. So can we conjecturally express this Mahler measure to go further? So there is no conjectural L function to which these Mahler measures appear to be related, as far as I know. But a very interesting paper by Borwein, Straub, Wan, and Zedilin related these Mahler measures to something completely different, which is the probability density of some random walk. So it turns out that random walks, so probability theory enters into the game, can be related to Mahler measures and also to hypergeometric functions. And in particular, these Mahler measures indeed essentially record how far, so the expected value of your distance from the origin if you work n steps in your random work very late at night. Okay, so the final example that I would like to mention is this polynomial in 3 variables, which was considered by Boyd and Rodriguez-Villegas in 2004, and later very deeply by Lyon, which shows that also some elliptic curves may appear in this exactness business. So here, this Mahler measure is conjecturally related to the derivative of the L function of an elliptic curve, which turns out to be the modular curve x1 of 15 at -1. Okay, so now here finally here we are at exactness. So why do we call polynomials exact, and what is this notion of exactness? Okay, so what happens in all the previous examples is that the framework that I outlined that was sort of contained in Deninger's work does not apply, because remember, we had this 3 conditions. VP had to be smooth, the polynomial had to be tempered, so this class needed to extend to some compactification, and the Deninger cycle, so this cycle gamma p needed to be closed, okay, so no boundary. And in all these examples, either this cycle has a boundary or VP is not smooth, okay? And so to deal with these cases, Vincent Maillot in 2004, he was participating in a workshop in Banff, and he gave a lecture where he hinted on that to deal with these cases, one should consider this variety, which is simply the intersection of the hypersurface defined by P and the hypersurface defined by the reciprocal of P. So the reciprocal of P is essentially the polynomial that you obtain by inverting all the variables. Okay, I mean, you need some extra care if the polynomial has complex coefficients because you need to take complex conjugation into account. Okay, and so why should this variety be interesting? Well, because it turns out that the boundary of the Deninger cycle, the boundary of this gamma p, is always contained inside this variety, okay? So in particular, if it happens that your polynomial is exact, and now I can finally give the definition for now, which is that this modular form that I showed you before, that was involved in Deninger's computation, is actually exact, which means that the corresponding cohomology class is 0, okay? Then, using Stokes' theorem, of course, you can write it. You can write the Mahler measure as the integral of some modular form of 1 degree less, and you can then restrict this modular form to WP over the boundary of this Deninger cycle. Okay, so this is the very simple idea. But now the interesting thing is that this WP is an algebraic variety, so we can work with it much better than we can than what we can do for the boundary of gamma p. Okay, and so this can be used already to explain Smith's identity, because in this case it turns out, so here is where the cyclotomic field q square root of -3 comes up, because it turns out that this intersection, so you're intersecting a line with a quadratic equation that you get from reciprocating, and it turns out that this intersection is indeed defined over q square root of -3, and here is where it's appearing. Okay, so now the question is, okay, so we did L2, what about L3? So how can we deal with L3? And so here comes the PhD thesis of Mathilde Lalin in 2007, so where she hinted at the notion of successive exactness. So the idea is that we want to apply Stokes' theorem once more. The problem is that we can't do that immediately, because of course, if you take the boundary of some cycle, then the boundary of the boundary will be 0, and so then the Mahler measure would be 0. So in order to do that, we need to take this closed cycle that we have, the boundary of gamma p, and sort of blow it up in order to make it acquire a new boundary. And indeed, this happens. So WP, and I will show you the explicit example of L3 later. WP, if WP is singular, then the pullback of this form omega to the desingularization of WP may become exact, and this boundary may become not closed. Okay, and so in this case, you just apply Stokes' theorem another time, and the degree of your differential form drops once more. Okay, and so for instance, I mean, Mathilde Lalin in her thesis, if you have a polynomial in 3 variables, she takes as WP tilde the resultant of P and the reciprocal with respect to the 3rd variable, and these in many cases can serve as a suitable desingularization of this intersection between the 2 hypersurfaces. Okay. Okay, so finally, in the last 15 minutes, let me talk about what we are actually doing. Okay, so how so we want to show that one can interpret exactness in a geometric way. Okay, or if you want, in a motivic way, call it how you want. Okay, so first of all, there is this thing that I mentioned before. So in Deninger's work, the Mahler measure is expressed as a period integral, but relative to something which is not algebraic. Where first of all, we show that one can express the Mahler measure as a period integral over a cycle which is closed. Okay, so in particular, if you take the variety given by the union now of VP and VP times, okay, and VP star, sorry, then you can express this difference of Mahler measures that appear thus in Deninger's theorem as an honest period where eta didn't change. So eta is always the regulator of this class, Z1, Z10. The only difference is that now you can't express so easily this cohomology class. So this will live, this will be a cohomology class which lives inside H n minus 1 thereon of V0, but you can't express it as easily with a differential form, because V0 will always be singular, okay, unless P is reciprocal. But okay.
So just a stupid question. This eta is always algebraic, the run? Because there was some logs in the expression you
right. No, yeah, right. So indeed, no. So I mean, it's real analytic. Yeah, it's real analytic theorem cohomology. Then I mean, of course, you can use various comparison isomorphisms to sort of write it down, I guess, as in an algebraic way, but the canonical representative that one has is not algebraic. Yeah. Thank you very much for the question. And and this is indeed an integral of this eta over a cycle, which you can obtain essentially by symmetrizing. So you use this involution that you use to define P star, and you symmetrize gamma p. Okay, and if you symmetrize gamma p, then it turns out that you obtain a cycle which has no boundary and lives in your singular cohomology of the complex points of V0. And if you pair it against eta naught, you indeed obtain the Mahler measure up to this correction factor. Okay, and so this is quite interesting now. Why? Because now we can look at the Meyer-Vittoris long exact sequence for the RAM cohomology. Okay, so V0 is defined as a union, and the intersection of these two pieces is really W. So it's really this variety which was introduced by Maillot. And so if our form eta naught turns out to be, so our, cohomology class eta naught turns out to be 0 on VP, then we get some class in the n-2nd de Rham cohomology of WP. Okay, and so in particular by the adjunction formula, okay, which the de Rham pairing respects, we can get the Mahler measure of P. Oh, sorry, here there is a typo. Here it should be an integral over WP. We can get the Mahler measure of P as an integral over WP. Okay, and this is exactly what was happening in Maillot's approach. Okay, so here we have, if you want, a second definition of exactness, which is essentially the same as with before. So P is exact if this cohomology class eta naught, when restricted to VP, is 0. Okay. And okay, just a bit of history here. So in his talk in Banff, Maillot pointed out that this involution, Zn goes to Zn minus 1, was used in this context of finding intersections with the unit circle already in some work of Darboux. So, and in the reports of this workshop, they point out to the date of 1875. So we haven't been able to find this work in the literature. So if you happen to know the works of Darboux better than we do, please reach out, and we will be very happy to find out where this involution appears. Okay. Okay. So now here is really the most interesting part. So how do we go on? So how do we explain this successive exactness, such as the one that we had for L3? Well, to do so, we need to change a bit mentality, let's say, or approach. So the thing is that this variety WP may not be always the good one, because there are some reciprocal polynomials. For example, this one, which appears in the family which was studied by Boyd, the one with the parameter k. So if you put the parameter k equal to 4, it turns out that actually the curve defined by the polynomial becomes singular, and this singularity is not avoidable as the ones that you have at infinity. Okay, and so in particular, it turns out that you can relate this Mahler measure quite easily to the L value of some Dirichlet character. So to explain this, we need to go a bit beyond the WP framework. And to do so, let us observe that WP generically is just the singular locus of V naught, because if P defines a smooth hypersurface, then P star will also define a smooth hypersurface. And if their intersection is transversal, then the singular locus of the union is just WP. Okay, so why not considering the singular locus instead? What does this mean? It means that instead of considering the Maillot-Vittori's long exact sequence for when we write V naught as VP union VP star, we actually we can consider squares of this type, so desingularization squares, where here we take the singular. So we start by taking a desingularization of V naught, okay, and then we take the pullback of W1, which, so here Wj is always defined to be the singular locus of Vj. Okay, so W1 is indeed the singular locus of V naught, and we just take the pullback, and we go on. So we can actually build a diagram like this. Okay, if you know about Hironaka resolution of singularities, of course you know that you can always assume that V1 is a divisor with normal crossings inside V naught tilde. If you do so, then there is a very combinatorial procedure to produce a diagram like this. Okay, it's essentially taking different disjoint unions of different intersections of the components of your divisor. Okay, and so what's really important here is this first square, because here we say that the polynomial is exact. Now, if the restriction of eta naught to V naught tilde, so not anymore to VP, but to V naught tilde, is equal to 0. Okay, so generically they will be the same, because V naught tilde will just be this joint union of VP and VP star, but these two notions can be different, and this one is a bit more general. Okay, and moreover, now this diagram allows us to finally define what it means to be successively exact by induction. So essentially, we say, so using this approach, one can say that a polynomial is successively exact if you can go on k times. So you say that it's k exact if it is k minus 1 exact, and and whenever you okay, sorry. So here, what you do is that at each step, you can consider a Maillot-Vittori's long exact sequence associated to these kinds of squares, okay? Because they are abstract blow-ups, so they induce Maillot-Vittori's kind long exact sequences. And so it turns out that if you're 0 on vk minus 1 tilde, you can always construct some class eta k in the cohomology of vk, okay? And then if this class will be 0 on vk tilde, then you will be able to construct a new class and so on, okay? And at each step, you can use the adjunction formula and write the Mahler measure as a pairing on your variety vk, okay? Which can be singular, but you can at least write it as a pairing on your variety vk. All right? There is a big caveat here, is that at each step, you have some ambiguity, right? Because whenever you choose a primitive, let's say in this way, in this long exact sequence, you have an ambiguity coming from the term that you have just before, okay? And so actually introducing these ambiguities it's not at all clear that this definition of exactness it's canonical. So in the works of Lyon and also before, this notion of exactness was somehow empirical. So the idea was a polynomial is k times exact if we can do it, if there is a way to do this process up to the kth step, but we would like something a bit more canonical than that. So this is why we turned to another idea, so which is essentially a more abstract version of the idea that I just mentioned before, which is just to look at the relative cohomology filtration. So very quickly, if we just change names for a bit, so we call X this V naught tilde, so this the singularization of V naught, and we call D this V1 inside of X, so this exceptional divisor, which we can assume to have simple normal crossings. Then, I mean, we introduce the usual notation, so we call the components D1 up to dr, and then for every subset I of 1 up to r, we call di the intersection of the corresponding components, which is smooth because the divisor is supposed to be simple, and we call di this joint union of the corresponding intersections where the set capital I has cardinality small I, okay? So if we did this, then as we all know, we have a spectral sequence which, starting from the cohomology of the various dp's, converges to the cohomology of X relative to D, okay? And so this spectral sequence in particular, I mean, the notion of convergence means that we have a corresponding filtration on the relative cohomology, okay? And so what happens now is that, remember that symmetrizing this Deninger cycle, we could write the Mahler measure as an integral here. Now the idea is that we can lift, since by dimension reasons, this cohomology group vanishes because WP is always affine, okay? Or actually, I mean, here, I mean, in full generality here, this should be the singular nucleus of V naught, if you want to be precise. So since this cohomology vanishes, then we can always lift in some way this eta naught to the relative cohomology group, okay? And this will be the only ambiguity that we introduce, actually, okay? So once we have introduced this ambiguity, and I mean, we have some hope of doing this more canonically than just looking at this long exact sequence, then we can push this through the isomorphism with the relative cohomology of X relative to D. And then one can simply say that the polynomial is k exact if this class eta tilde that we constructed lies in the kth step of this relative cohomology filtration. And why is this interesting? Because, well, if your polynomial is indeed k exact, and if it happens to be not k plus 1 exact, okay, and if you also have some condition on the corresponding cycle, okay, so this did not happen before, but now it's it's sort of crucial because we will get some integral over a smooth variety. So it's crucial to assume also something on your cycle, namely that your cycle lies in field k minus field k minus 1 of the corresponding homology filtration. Then what happens is that you can express the Mahler measure as a pairing on the graded pieces for these filtrations, and this turns out to be just a pairing on the smooth variety dk. Okay, so indeed we have achieved our goal. Our goal was to say that whenever we have a polynomial which is k exact, we can sort of reduce the dimension of k steps and compute the Mahler measure as an absolute period of a smooth variety of dimension k times less. And this is indeed what one manages to do with this new definition. Okay, so here is very quickly, if I may take a couple of minutes, Tiago, if that's okay. Here is very quickly how, for example, one can explain this three-variable linear polynomial of Smith. So here is a very nice picture that one can draw. So it turns out that in this case, if you take this linear polynomial, then VP will just be A2 minus Z, where Z is the union of three lines. So it's the two coordinate axes and this line here. Okay, so this is Z, this is the line that you're removing from A2 to get VP. Then it turns out that WP, so the intersection of VP, so here we're in the generic case, VP and VP star are smooth, okay? So it turns out that WP will be just another, so maybe let me draw it in blue, another union of lines, namely now you take, oops, now you take x equals 1, y equals 1, and x plus y equals naught. Okay, so you take essentially another union of three lines, which sort of is symmetric to the first one. Okay, and this will be WP up to removing Z also from this. And so this means that you can compute all your cohomology groups very explicitly. So H2 and H1 of VP will have dimension 3 because you're removing these three lines. Then H1 of WP will have dimension 4 with three components coming from the restriction from VP, and one which is given by the cycle that you can draw inside the triangle. Okay, and then it turns out that you can also compute the image of the Maillard-Vittoris map, which means that you can compute H1 and H2 of V0. And once you have all that into place, you can compute the filtrations inside this cohomology group. So it turns out that this cohomology group will have dimension 8, okay, from these long exact sequences. And inside it, this filtration will, so the field 1 and field 2 will coincide. And this is due to the fact, essentially, that all the components of WP are rational varieties. So you have no condition in assuming that the cohomology class will restrict trivially to these components. So these two, it turns out that these two pieces of the filtration actually coincide. And when you get to D2, you actually get 6 points, which are all defined over Q, okay? And this is precisely, since all these points are defined over Q, this is precisely where the zeta function, where the Riemann zeta function appears, okay? And one can actually really prove the identity on the nose by sort of keeping track of all the primitives that one is choosing, okay? So to conclude, okay, here is a very long list of sort of things that might be interesting to look at, okay? So for example, well, first of all, we would like to resolve this ambiguity that comes from that we have for the choice of eta tilde. Then we would like to compactify the whole situation. So write the Mahler measure as a period over some smooth projective variety minus one normal crossing divisor relative to another normal crossing divisor. Okay, and we can do this. One usually does this by compactifying using the Newton polytope of the polynomial P. One can compare these filtration on XD with the weight filtration on V0, and this would be great on the one hand because it's essentially more canonical, but on the other hand, this weight filtration keeps also track of the fact that V0 is not compact. Then one could also compare this with the degeneration P times P star equals to T. So these will be sort of generically smooth, and then when T goes to 0, it becomes singular. So maybe there is something to look at also there. Then there is this problem that this cycle gamma p is maybe a bit ad hoc, and so maybe there is a way to make it more canonical following the work of Besser and Deninger from the 90s. Finally, computing more examples, so these families Ln and these families considered by Mathilde Lalline, which should be n-1 exact. And the last thing would be really to express this Mahler measure as a motivic period, as we have seen before, so which is related to the second point, following the work of Brown. And actually, maybe since we are integrating the logarithm of an absolute value, this might be a single varied period, okay? So single varied periods have appeared already in this seminar quite a lot, so I thought it might be worth to mention them. And finally, one would also like to study these sort of questions in families. And there is a very interesting work of Doran and Kerr on the K-theory of hypersurfaces on that. And finally, this question that we had in the beginning. So via the period conjecture, can we compute, if I give you a bunch of polynomials, the transcendence degree of this extension when defined over Q? This is the question that I leave you with, and I thank you very much for your attention.
Thank you very much for this very nice talk. Let's thank Riccardo. Questions?
Maybe Riccardo, in your theorems, exactly at which step you see the relation with the derivative of the L function? I think you mentioned very brief.
Right. Yeah. So it's essentially at the last step. So essentially, when you if these conditions are satisfied, then you can write your Mahler measure as a pairing over this smooth variety dk. So there is one last step to be taken, which is that this dk here need not be compact. Okay. So I mean then one so in explicit situations one knows how to compactify decay. So if you can show that the residues of the classes that you have constructed here, eta k tilde and gamma k tilde, sort of vanish at infinity. So I mean it's really eta k tilde that you have to look at. So if this class extends to the compactification, then you will have a smooth compact variety. So, and in particular, you will have an associated L function. So here this will be a pairing over. So if you use the Lyon cohomology, it will be a pairing over h n minus one n minus k and the Lyon. Sorry, h n minus k the Lyon of dk Rn. Okay, and so so the regulators in this cohomology are essentially related to the L function of, let's say, the motive, quote unquote, hn minus 1 minus k of dk at the value m again. Okay, so here I am essentially assuming that we have no residues. So if you remember, there was this case of a 4-variable polynomial whose Mahler measure turned out to be related to an L value at s equal to 3. So I am assuming that we're not in this case. So if we are not in this case, then you would essentially see this L value appearing, yeah, for your Mahler measure. Or sorry, and maybe here you need to take some dk bar in order to have really some smooth and proper variety to which you can apply Beilinson conjectures.
Any other questions?